For thousands of years, human travel was constrained by strict biological limits. You either moved at the speed of your own 2 feet, or you relied on massive, heavy animals to drag wooden carts through the mud. What ancient civilizations lacked was a middle ground. They needed a lightweight, personal vehicle that could amplify a single person's physical energy without requiring a pasture full of feet to keep it running. Early engineers began experimenting by shifting human weight onto simple, rolling wooden axes. These initial prototypes were crude, heavy, and incredibly difficult to steer. In 1817, Carl Dreis introduced the draisine, or running machine, a design that proved a rider could balance in line on 2 wheels and coast. But the draisine lacked any propulsion system. To move forward, the rider straddled the wooden frame and pushed directly against the dirt with their feet to build momentum. The biomechanics were punishing. Dragging a solid wooden frame along unpaved roads generated immense friction, rapidly exhausting the rider over any real distance. While Dreis proved 2-wheeled balance was possible, his design left the basic problem of propulsion unsolved. Riders still relied on the ground for momentum. The first solution arrived in the 1860s. Inventors attached rotary pedals directly to the axle of the front wheel, allowing riders to lift their feet off the street entirely. This direct drive system came with a strict physical limitation. 1 full rotation of the rider's legs equaled exactly 1 rotation of the wheel. The vehicle's top speed was strictly capped by the size of the wheel itself. To go faster, Victorian engineers made the front wheel massive. This design, known as the Penny-Farthing, allowed the rider to cover far more ground with every single pedal stroke. That extra speed came at a severe physical cost. Putting the rider's center of gravity directly over that towering front axle meant that a single rock or sudden stop would launch them headfirst over the handlebars. By prioritizing raw speed over basic safety, inventors built a machine that was largely unrideable for the general public. To make the bicycle viable, the power source had to be separated from the wheel size entirely. The answer was the safety bicycle. It brought the rider back down to earth on 2 equal-sized wheels. This diagram illustrates the core engineering breakthrough, the chain drive. By decoupling the pedals from the wheel axle, engineers could use a large front sprocket to turn a smaller rear sprocket multiple times per pedal stroke, multiplying force. Adding multiple rear cogs allowed riders to shift between sizes, altering mechanical advantage to maintain rhythm while climbing hills. Around the same time, solid rubber gave way to the pneumatic tire. These air-filled tubes absorbed the bone-rattling vibrations of cobblestone streets, drastically improving rider comfort. Factories began mass-producing this highly efficient design, sparking a global phenomenon. Cycling quickly became an elite competitive sport, while simultaneously filling city streets with commuters. The safety bicycle gave the working class a fast, reliable, and affordable way to navigate their cities independently, permanently expanding the radius of daily life. As infrastructure expanded through the late 20th century, the core diamond frame began to branch out, adapting to highly specific environments. Engineers developed the mountain bike to conquer unpredictable off-road terrain, equipping it with heavy-duty suspension systems and aggressive tire treads to maintain grip. Yet for mass urban commuting, a biological limit remained. Despite perfect gearing, raw human stamina still struggled against the long distances and steep inclines of sprawling modern cities. The modern electric bicycle bridged that final gap. By integrating lightweight, high-capacity batteries directly into the frame, engineers provided a secondary power source. Pedal assist smart sensors measure the exact wattage a rider puts into the crank, immediately blending that human effort with motorized torque. By solving the exhaustion factor, the exact problem that plagued Carl Dreis in 1817, the e-bike offers a sweat-free commute that directly competes with the automobile. Moving into the near future, the bicycle is transitioning from an isolated mechanical tool into a hyper-connected component of intelligent urban infrastructure. Engineers are integrating active AI systems, projecting augmented reality navigation displays directly into the rider's field of view, and utilizing self-balancing gyroscopes to prevent falls. Material science is pushing the frame itself further. employing ultra-lightweight carbon composites and embedding structures with renewable solar charging capabilities. This timeline charts that continuous climb in mechanical efficiency. We can track an unbroken line of energy amplification, starting directly from a wooden running machine and pointing toward AI-assisted transport. Even in an era defined by aerospace engineering and autonomous cars, we consistently return to refining this simple two-wheeled format. It provides an unmatched balance of human agency, mechanical advantage, and spatial efficiency. Bicycles have transformed from simple wooden frames into intelligent mobility networks, remaining one of humanity's most enduring and effective inventions. We often treat this machine as a simple tool, yet it is arguably the most efficient human-powered vehicle ever devised. The challenge of making it move starts with a deep physical mismatch. Our biological mechanics are not naturally configured to drive a rotating axle. Human legs are optimized for walking and running, a process that relies on a piston-like linear thrust pushed directly into the ground. This creates a structural barrier between our anatomy and the machine. To move, the bicycle must first resolve this conflict between flesh and steel. The geometry is the problem. Human movement is linear, but a wheeled machine requires perfect circular motion to operate. If you feed a straight downward thrust into a circle, the energy hits a dead spot. The momentum stutters at the bottom of every stroke. For the machine to work, an intermediary must translate the physical language of a straight line into the language of rotation. This translation is the sole purpose of the pedal and crank assembly. This is the starting point of the kinetic chain, the rider's leg positioned directly over the bike's drive center. The quadriceps and calves contract with intense pressure, generating a sudden surge of kinetic energy. That energy is funneled into a singular downward strike. This is the critical threshold, the millisecond where biological force attempts to enter the mechanical system. Without a way to capture this power, downward force simply pushes the bike into the dirt. The flat platform of the pedal provides the interface where that energy finally exits the body. Here, the crank arm acts as a rigid lever on a fixed central pivot. As the rider pushes, force travels down the arm. The fixed pivot forbids energy from continuing downward, forcing the linear thrust to redirect into a curving trajectory. This forced redirection is the moment biological thrust is transformed into mechanical torque. The newly created torque is immediately offloaded into the large-toothed gear, the chainring. The chainring's geometry is built to withstand the immense stress of the rider's output, locking into the circular motion. Within this component, the motion is now purely mechanical. It is now entirely independent of the original walking motion of the leg. The spinning chainring represents the successful conversion of human effort into machine power. The crank system serves as a biomechanical bridge. Using a simple arrangement of levers and pivots, it reconciles the conflict between our anatomy and the requirements of the wheel. This continuous translation is the foundation of all human-powered transport. The system is now fully active. Rotational energy is spinning the chainring and pulling the metal links of the chain. But spinning a metal ring in the center of the frame does not actually move the rider forward. If the energy is stuck in the middle of the bike, how does this moving chain pull the entire machine across the ground? A bicycle, when completely isolated from its natural environment, dramatically reveals the hidden underlying mechanics of its operation. Fading away the chassis and wheels leaves only the core power delivery components, the drivetrain. The design of this system is dictated by human physiology. We evolved for walking, a low-speed, reciprocating motion, where legs push up and down in alternating steps. Wheeled vehicles demand the opposite physical input. To overcome rolling resistance and aerodynamic drag, they require continuous rotational torque. The drivetrain acts as an impedance matcher, bridging the gap between reciprocating human motion and the rotational requirements of a wheel. It exists to convert fluctuating biological oscillation into smooth mechanical rotation. The process begins at the front of the drivetrain. The pedals and crankset act as the primary input stage. The crank arm operates as a simple lever, forcing a linear physical input into a fixed circular path. As the rider pushes down, the leg applies a linear force vector directly into the pedal spindle. This graphic illustrates the mathematical reality of that motion. Rotational force, or torque, is only generated by the portion of the downward push that is perpendicular to the crank arm. As the angle changes, the torque output fluctuates. Mechanical efficiency peaks when the crank arm reaches 90 degrees. At perfectly horizontal, the full downward force vector is perpendicular to the lever, hitting the peak of the equation's sine wave. Conversely, the system hits mechanical dead spots at 0 and 180 degrees. When the crank is perfectly vertical, a downward push yields exactly zero torque. Applying this pulsing torque profile directly to a drive wheel would cause the vehicle to surge and stall with every pedal stroke. The chainring captures this variable energy and prepares it for transmission. By fixing the lever to a continuous circle, the crank acts as a mathematical filter, transforming an uneven biological push into a usable rotational force. From the chainring, that captured energy transfers into the chain. Despite appearances, a bicycle chain does not push the rear wheel or transfer energy as a rigid body. Looking at this complete loop in motion, the rotational torque at the chainring is converted into linear tensile force. It is pure pulling energy. 100% of the rider's mechanical power is transmitted through the upper span of the chain. The bottom return span carries no tension and performs no mechanical work. To manage this tension without snapping the metal, we examine the micro-mechanical interaction where chain rollers seat into the grooved teeth of the chainring. These teeth are cut with a specific geometric curve known as an involute profile. This involute geometry dictates the path the chain rollers take as they enter and exit the teeth under load. The shape prevents the metal components from binding, keeping friction low enough that mechanical efficiency regularly exceeds 98%. The chain functions as a tensile bridge, ensuring the biological power captured at the crank reaches the rear wheel with minimal loss. That tensioned upper chain terminates at its final destination, the rear cassette. Climbing a steep hill requires a different mechanical advantage than maintaining speed on flat asphalt. Without adjustment, the rider would stall out against high resistance. Gear ratios provide dynamic, adjustable levers that allow the rider to manipulate their mechanical advantage on the fly. This analytical model compares those levers under two extreme conditions. On the left, a climbing setup uses a small chainring pulling a massive rear cog. On the right, a high-speed setup uses a massive chainring pulling a tiny rear cog. In the climbing scenario, a small input radius pulling a large output radius acts as a torque multiplier at the rear axle. Generating that torque requires a sacrifice in rotational speed. The rear wheel turns slower than the pedal input. Shifting to the right screen, the math reverses. A large input radius pulling a small output radius sacrifices rear wheel torque to act as a speed multiplier. In this speed scenario, a single revolution of the pedals forces the rear wheel to spin multiple times. Gearing allows for a precise manipulation of resistance. By adjusting the gear ratio, the rider maintains their peak biomechanical power output, the ideal cadence, regardless of the slope's gradient. Gear ratios decouple the speed of the rider's legs from the speed of the vehicle, allowing operation at peak efficiency on any terrain. Reassembling these systems back into the studio environment rebuilds the complete structure. Bringing the mechanical system up to full operational speed visualizes the continuous, dynamic flow of energy through the machine. In this X-ray view, biological force enters the pedals, converting into rotational torque around the crankset. This becomes linear tensile force, pulling the upper chain. The rear cassette modulates this force, turning the wheel to create tractive force, pushing backward against the ground. The bicycle drivetrain resolves the mismatch between walking mechanics and aerodynamic velocity, forming a closed kinematic chain that extends human capacity through mechanical advantage. The energy reaches the rear wheel, but a critical question remains for next time. How does this rapidly rotating chain actually move the bicycle forward? The gears have caught, the chain is pulling, and the wheels are blurring the pavement. We have achieved velocity. But an object moving rapidly in a straight line with no capacity for correction is a crash waiting to happen. Left to itself, this mass of metal and rubber is entirely unstable. It is caught in a physical crossfire. Forward momentum drives the mass ahead, while gravity constantly pulls the frame down toward the asphalt. Navigating this conflict requires a mechanism that can take raw kinetic energy and actively tame it, keeping the entire structure upright. Generating propulsion is useless if you lack the physical systems required to guide and stabilize it. The solution lies at the front of the frame. The handlebars form a rigid, uninterrupted connection straight down through the steering column, directly to the front fork and the front wheel. Rotating those handlebars manipulates the machine's center of gravity. As the wheel angles, the rider shifts weight in tandem with the steering input. These microscopic adjustments keep that center of gravity hovering precisely over the narrow contact patch where the tire meets the ground. During continuous weight shifts, the rubber compound of the tire bites into the road surface, gripping the pavement to prevent the wheel slipping sideways. Staying upright is never a passive state. It is an active, continuous mechanical negotiation between human steering inputs and the laws of physics. Guiding speed solves the balance problem, but you also need the capacity to arrest that motion on absolute command. Deceleration begins with physical human input at the brake levers, mounted directly beneath the rider's fingers. Squeezing that lever pulls on braided steel cables running along the frame, translating biological force into mechanical tension. That tension travels the length of the bike, arriving at the disc brake assemblies anchored firmly to the center of the wheel hubs. Here, the mechanical cable forces the brake calipers to clamp shut. Dense brake pads are driven forcefully into the sides of the spinning steel disc. The entire braking system operates as a mechanical amplifier. It takes a slight squeeze from 2 fingers and multiplies it into enough physical force to stop a human body hurtling forward at 30 miles per hour. Mechanically speaking, brakes do not actually stop motion. They destroy momentum. They achieve this by inducing extreme friction between the brake pads and the spinning disc, actively converting kinetic energy into thermal energy. This chart maps the exact physics at play during a hard stop. You can see the velocity curve dropping sharply, completely offset by a massive, immediate upward spike in temperature at the point of contact. The motion hasn't disappeared. It has simply become heat. While this violent, high-friction activity occurs at the hub, the tire rubber down on the asphalt must maintain static friction, refusing to slide, so the bike doesn't enter a dangerous skid. The immense stopping force transfers outward from that central hub disc, travels down the tensioned wheel spokes, and anchors firmly into the road surface. Executing a safe stop is a masterclass in thermodynamics, successfully dissipating the massive kinetic energy of the rider entirely into the air and the asphalt. Zooming out, we no longer see isolated components. We see a single, holistic machine. The propulsion system, pedals, chain, and gears, re-engages to build speed. Simultaneously, the steering column continuously balances the frame, reacting to the pavement. Every structural component locks into a unified cycle, maintaining a continuous loop of generating, guiding, and arresting motion. This seamless harmony of independent mechanical systems grants the rider complete physical mastery over kinetic energy. The result is a machine that feels effortless to the person in the saddle, carving quietly through the landscape. True engineering greatness is often disguised by the familiarity of everyday objects.